So we'll now learn about circle. So how is a circle represented? So to represent a circle, we represent a circle in the form of equations, and equations are in various forms. So we'll represent a circle in various equations, and the equations for representing a circle are as follows. The first equation being the center radius form. This is the first equation. And how is a circle represented in the center radius form? So if P x y is a point on the circle, so this is a point on the circle, then the equation of the circle would be a with center at the origin and radius a as x square plus y square is equal to a square. So if there is a point a, and if the center is at the origin, so if the center is, we'll consider center o 0 0, so this is the center, then what would be the equation of the circle? So this is basically the equation of the circle with the center at the origin at any point p x y. And if suppose it has a center, the center of the circle is hk and the point is pxy, then the equation of the circle and the radius is r, then the equation would be x minus h the whole square plus y minus k the whole square is equal to r square. So so in the center radius form, the center is given. So if the center is 0 0, then the equation would be this, and if the center is hk, then it could be any center. So the equation of the circle would be this, where x and y are the points p, are the coordinates of the point p, and a is the radius here, and r is the radius here. The second equation is nothing but the parametric form. The parametric equations of, so we now know that the center radius form is x square plus y square is equal to a square. So x is equal to, we know that in parametric form x is equal to a cos theta and y is equal to a sin theta, where theta is a parameter. We know that theta is basically a parameter. So x is equal to a cos theta and y is equal to a sin theta. So what we do is that the parametric equations of the circle becomes x minus h the whole square plus y minus k the whole square is equal to r square r. So the equation, so this is the equation in the center radius form. So this equation in the parametric form would be x is equal to h plus r cos theta and y is equal to k plus r sin theta. So this is basically the parametric form of the equation of the circle. So the next form being the diameter form. So the next is the diameter form. So if there's a point p xy on the circle, so this is a point p on the circle, then the equation of the circle described on the line segment joining the points x1 and x1 y1 and x2 y2 as a diameter r. So if suppose this is a circle and this is x1 y1 and x2 y2, then the equation of the circle would be x minus x1 x minus x2 plus y minus y1 y minus y2 is equal to 0. So this is basically the a diameter, this is the diameter form of the form of representing the circle. Now coming to the general form of equation. So the general equation to represent a circle is written as x square plus y square plus 2gx plus 2fy plus c. So now we'll know what are these gx, fx, fy and c. So for this circle, the center is nothing but minus g and minus f. So we come to know that what are g and f. So the center is nothing but minus g and minus f. So from this equation we come to know that minus g and minus and f are the center, and therefore the radius would be, radius is root of g square plus f square minus c. So this is nothing but the formula for the radius of the circle. This is nothing but the center of the circle. So now we'll come to see the important aspects in a circle. The first one being a secant. So what is a secant? A line which intersects the circle into two distinct points is known as secant. So this is a circle. So this line divides the circle into two distinct points. So this is basically a secant. Next is a tangent. So what is a tangent? The limiting position of secant PQ is a tangent as Q tends to P along with the circle. The point P is called the point of contact of the tangent. So this is the circle. So this line just touches the circle, and this point of contact is nothing but P. So this is nothing but the tangent of the circle. So this line is nothing but the tangent of a circle. So now we'll see the normal of a circle. What is a normal? Normal to a circle at point P. So this is at point P is a line through the point P perpendicular to the tangent. So this was a circle, this is the tangent, and this is the point P. So the line perpendicular to the tangent, so line perpendicular to this, it makes a 90-degree angle. So this is the normal and this is the tangent. So now we'll see the equations of a tangent at a point. So equation of a tangent at point P x1 y1 on circle x square plus y square is equal to a square. So we have been given a circle whose equation is x square plus y square is equal to a square. So we have to now find out the equation of a tangent at a particular point P x1 y1. So we'll just represent the circle and a tangent. So this is the circle, this is a tangent. Okay, so this is the tangent at point, this is the point P x1 y1. Okay, and we have considered the equation x square plus y square is equal to a square. That means the center is nothing but 0 0. So this is the center 0 0, that why we have considered. So this is O and this is P. So what is the slope of P? X1 x2 minus x1 upon y2 minus y1. So slope is y1 minus 0 upon x1 minus 0 is nothing but y1 by x1. So since OP is perpendicular to the tangent, that means the slope of tangent is minus x1 upon y1. We came to know the slope of this y1 x1. The slope of a line, and so slope of a line perpendicular to it is nothing but a negative of the reciprocal of it. So slope of tangent would be negative of reciprocal of this. Okay. So now what we do is, so the equation of a tangent to circle at point P is y minus y1 is equal to m x minus x1. So this is basically the equation. Now what we do is we substitute the value of slope here, that is y minus y1 is equal to minus x1 upon y1 upon x minus x1. So after solving this, what we get is x1 plus y1 is equal to x1 square plus y1 square. So this is basically the equation of a tangent of a circle at a point P x1 y1, and circle is this. So therefore x1 square plus y1 square is nothing but a square. So thus equation 1, so what we come to know is that x1 plus y1 is equal to a square. We substitute the value of x1 square and y1 square to get a square, because x1 square plus y1 square is nothing but a square. So we substituted in that the formula, and that's why we got x1 plus y1 is equal to a square. So this is basically the required equation of a tangent at point P x1 y1. So now we'll see the equation of a normal to circle at any point. So we'll consider a circle. So this we'll equation of a normal. So to find the equation of a normal to the circle, so this is the equation of the circle given to us: x square plus y square is equal to a square. So at any point P x1 y1. So what we have to do is to find the equation of a normal to the circle this at any point p x1 y1. So how will we find it? So the equation of the circle is nothing but x square plus y square is equal to a square. So now we differentiate this equation with respect to x. So what we get is 2x plus 2y dy by dx is equal to 0, a square constant. So dy by dx is equal to minus xy. So what we got here is nothing but the slope of the tangent, because dy by dx is nothing but the slope of the tangent. So now what we have to find is the normal is basically perpendicular to the tangent, so the slope would be reciprocal of negative of this. So the slope of the normal is nothing but is equal to nothing but y1 by x1, because it is at point y1 x1. So this is basically the slope of the normal. So now what we have to find is that the equation of the normal to the circle at point p1 x1 y1 is, so now what we do is in the equation we substitute its value, that is y minus y1 is equal to y1 upon x1 x minus x1. So this is the equation, and that here we have put the value of the slope of the normal, that is y1 by x1 at point x1 y1. So now what we do is now we put x1 to this side, so x1 y minus y1 is equal to y1 x minus x1. So now after substituting and after reshuffling, what we get is x by x1 is equal to y by y1. So this is basically the equation of the normal. Now we'll find the equation of the normal in the parametric form. So we'll find the equation of the normal in the parametric form. So we have the circle x square plus y square is equal to a square. In the parametric form, p theta is equal to a cos theta and a sin theta. So this is the parametric form. So what we now do is let x is equal to a cos theta and y is equal to a sin theta. So now what we do is now we differentiate with respect to theta. So dx by d theta is equal to minus a sin theta, and dy by d theta is equal to a cos theta. So now what we have to find is dy by dx, that is the slope of the tangent. So dy by dx is nothing but a cos theta upon minus a sin theta, that is nothing but minus cot theta. So this is basically dy by dx minus cos theta minus cot theta. Dy by dx is nothing but the slope of the tangent. So what is the slope of the normal? Is equal to tan theta. So tan theta is nothing but the slope of the normal. So now equation of the normal is given by y minus a sin theta is equal to tan theta x minus a cos theta. So now what we do is, so tan theta is nothing but sin theta upon cos theta. So after solving this equation, what we get is y is equal to tan theta x. So this is the equation of the normal in the parametric form. Conics. In conics, we learn three types of curves that are conics, that are the hyperbola, the parabola, and the ellipse. So these three conics we'll learn in this chapter, that is the hyperbola, parabola, and the ellipse. So the first and the important concept in this chapter is basically the eccentricity. So if the eccentricity of the curve, that is E, is greater than 1, that means it is a hyperbola. If the eccentricity is equal to 1, that means that it is a parabola. And if the eccentricity is less than 1, then it is an ellipse. So these three are the basic points that we see in this chapter. Now we'll come to a very important concept, that is we'll find the equation of the tangent equation of tangent and normal to any point x1 y1 in the parabola. Okay, so we have been given a parabola. Okay, and we have a tangent on it, and then it's normal. So what we have to find basically is the equation of the tangent and the normal at any point p x1 y1. So we'll consider a point p x1 y1 where the tangent touches the parabola. So the parabola that we consider here is y square is equal to 4ax. So this is the parabola given to us. We have a tangent and the point is p x1 y1. So the equation of a tangent is y1 is equal to 2a x plus x1. So this is basically the required equation of a tangent at a point x1 y1, where x1 and y1 are basically the coordinates of the point where the tangent touches the parabola. Okay, and a is what a is given here, and the equation of the normal, this is the equation of the tangent, and the equation of the normal at point p x1 y1 is y minus y1 is equal to minus y1 upon 2a x minus x1. So this is basically the equation of the normal at a point p x1 y1, and this is basically the equation of the tangent. So now what we find is that equation of the tangent and normal to the parabola, we'll find the equation of the normal and tangent parabola at pt, at p bracket t, where t is a parameter. So now first we had find out the equations in the equations in the point form, and now we'll find where the parameter is given, that is t is a parameter that is given to us. So the equation of the tangent in the parametric form is y is equal to 1 by t x plus at. So this is basically the equation of a tangent where t is basically the parameter. So this is the equation of the tangent in the parametric form. Equation of the normal in the parametric form would be y is equal to minus tx plus 2at plus at cube. So this is the equation of the normal where t is the parameter given to us. Ellipse. So now what we do is we will find out the equation of the tangent and normal to the ellipse. So the equation of the ellipse has been given to us, that is x square upon, this is the general equation of the ellipse, x square upon a square plus y square upon b square is equal to 1 at a point p x1 y1. So this is the general equation of the ellipse, and this is a point given to us. So what we have to find is that the equation of the tangent and normal to the point. So the equation of the tangent comes out to be x1 upon a square plus y1 upon b square is equal to 1. So this is basically the equation of the tangent to the ellipse at point x1 y1, and here x1 y1 are nothing but the coordinates of the point, and this is the equation of the tangent. Now the equation of the normal to the ellipse is a square x upon x1 minus b square y upon y1 is equal to a square minus b square. So this is basically the equation of the ellipse. Now we have found out the equation of the tangent and normal. Now we'll find out the equation of the tangent and normal to the same ellipse in the parametric form, where so this is x square upon a square plus y square upon b square, and at p theta. Okay, so the equation of the tangent becomes to be x upon a cos theta plus y upon b sin theta is equal to 1. So this is the equation of the tangent at p theta, Now the equation of the normal at p theta is ax upon cos theta minus by upon sine theta is equal to a square minus b square. So this is the equation in the equation of the normal. So now we'll find out the equations of the tangents, the equation of tangents in terms of slopes, where m is a slope given to us. So now we'll find out the equations of the tangents and normal, the tangents where m is a slope being given to us. So in parabola, so in a parabola, the equation of the tangent to the parabola in terms of slope m. So we have been given a parabola, so we have to now represent the parabola in the form of the equation where slope m is given to us, and the point of contact is c upon m comma 2a by m, that is a upon m square 2a by m. So this is the point of contact where the tangent touches the parabola. So the equation of the tangent that we get is y is equal to mx plus a by m. Now what we do is we'll find out the equation of a tangent to the ellipse x square upon a square plus y square upon b square is equal to 1. This is the equation of the ellipse. Now we'll find out the equation of the tangent to it in terms of slope. So and the point of contact. So the equation is y is equal to mx plus minus root of a square m square plus b square. So this is the equation of the tangent where m is basically the slope. So we have represented the tangent in the form of in terms of the slope, where the point of contact of the tangent and the ellipse is minus a square m upon c comma b square upon c. So this is basically the point of contact of the tangent and the ellipse. Now we'll find out the equation of the tangent of the hyperbola. So x square upon a square minus y square upon b square is equal to 1 in terms of slope. So this is the equation of the hyperbola, and we have to find out the equation of the tangent. So the equation of the tangent here is y is equal to mx plus minus root of a square m square minus b square. This is the same as the equation of the ellipse, just that here it's plus, and in hyperbola it is minus, so it can be remembered very easily. So the equation is y is equal to mx plus minus root of a square m square minus b square, where m is the slope and we have represented the tangent in the terms of slope, and the point of contact is nothing but minus a square m upon c comma minus b square c. So now we have represented all the equations of the tangents of all the three curves, that is the parabola, ellipse and the hyperbola, in terms of their respective slopes and their point of contact of the tangent and that particular curve.